All right, class. I wanted to just do a couple of practice problems, just in the same space of momentum and energy problems. Just kind of work through a couple of these and talk through some of the strategies. Okay, so here's our first one. I've got a little bullet here. It's half a kilogram going 100 meters per second. It blows into this 20 kilogram block and it hits it hard enough, or the block is made of weak enough stuff that the bullet comes blasting out the other side. Now it's lost some velocity, right? It comes out the other side only moving 20 meters per second, and then it continues on and hits this wall. But right, we know a thing or two about conservation of momentum. When this thing goes ripping through it, it's going to be applying a force over a time. There's a backwards impulse on the bullet, a forwards impulse on the block. We know those two impulses are the same. Anyways, this block is going to be moving after the bullet goes whizzing through it, right? So, but the question here says, okay, how much does the block compress the spring, right? Block is initially at rest, bullet goes blasting through it. The bullet doesn't compress the spring at all, but the block is going to slide over here and hit this spring. And we want to know, okay, well, how much does the block compress the spring? So, okay, well, where do we start? What's going on? Is there an energy piece? Is there a momentum piece? And the fact that there's a spring in here tells you energy is going to come into play somewhere, and there's a collision, so momentum is going to come into play as well, right? So the momentum, the collision happens first, so we want to start with a collision, okay? So is this a conservation of momentum situation? And it is, as long as you include everything that bumps, right? There are forces acting between the block and the bullet, but those are all third law pairs, so they live inside the system, okay? So here we go. So the initial momentum of the system is going to be equal to the final momentum of the system. So we're looking at like right before the bullet hits the block and then right after the bullet hits the block. Where's all the momentum to start with? Well, it's in the bullet, right? The block isn't moving. It has no momentum. It's all in the bullet. Afterwards, they're both moving a little bit, so they're both carrying some of that momentum, okay? So here we go. So I've got the momentum of the two things before, the momentums of the two things afterwards, and then I plug in my numbers, right? Here's the bullet. It's going really fast. No momentum in the block. Has to be equal to what's going on afterwards. Here's the bullet again, still going 20 meters per second in that same positive direction, right? Both of these are positive. And then here's my block, right? 20 kilograms moving at some speed. We need to figure that out, right? I know everything but the velocity, so a little bit of algebra later, right? Multiply these, subtract it over, divide by 20, right? We're looking at 2 meters per second for the block, okay? Okay, so boom, I got the velocity of the block. There it is, 2 meters per second after the collision is the velocity of the block. So now how much does it compress the spring? The bullet doesn't hit the spring, so I don't care about the bullet anymore, right? It's just the block, right? I've got the block moving along at 2 meters per second. This is a marvelously frictionless surface. And so now it's an energy problem, okay? So now, right, time for the energy approach, okay? So here's my equation. The initial energy in the system, that mechanical energy, plus any work done in between is going to be equal to the final energy, okay? So there's no friction. Before I'm here, all the energy is kinetic, right? There's no spring right here. It's not above the ground. It's just moving. All of the energy is kinetic. At the end, I'm still not above the ground. I'm going to compress the spring as much as I can. So right, that block is going to come to rest. There'll be no kinetic energy, right? So all of this kinetic energy is going to become elastic energy stored in the spring, okay? So that's where we are with this problem right now. And so let's plug in the numbers we know, right? 20 kilogram block, 20 kilogram block, going 2 meters per second, compresses the spring, solve for x, okay? We know everything but x. I run through my calculation, and I'm gonna compress that spring 0.73 meters, or somewhere thereabouts. Okay, so so that's that problem, right? We kind of ran through that really fast. I didn't warn you at the beginning, but hopefully you took a second to try and work through some of this yourself. But that's kind of this first problem. This one is pretty straightforward. This is something that you could see in the homework or that you could see on an exam, right? This is a straightforward enough problem that you have the tools to solve, okay? Now this next one, this is a little bit more complicated, right? There's a little bit more going on here. But we're going to walk through this, right? I want to look at this more complicated problem just so that we have some tools that we can think with, okay? So, here's the opening scenario, right? I've got this block up here. sitting on this incline, and all this incline is, and the track is frictionless, right? So this is going to slide down, and it's going to slam into this spring, and this block is going to start moving. So this thing is going to slide down, it's going to slam into the spring, and some crazy stuff is going to happen, and that's kind of what we want to talk about, okay? But as you're looking here, I'm giving you a height. You see this thing is going to come down. That should be screaming, oh, I can use conservation of energy to find the velocity of block M right here at the bottom of the ramp. And then this thing's going to hit the spring, and both of these things are going to start moving, and maybe some of the energy is going to, right? Energy is going to go into the spring. There's going to be kinetic energy in the blocks, right? There's a lot going on. So let's see where we're going with this, right? So my first question is, well, just in this system of the two blocks and the spring and the Earth, right? How much energy is there? And okay, well, in the beginning, right? There's a spring there, but it's not compressed. It's just sitting there, right? The 7 kilogram block has no energy. All the energy is this gravitational energy right here, okay? And the other question I'm asking in the beginning is, how fast is block A going when it gets to the bottom of the hill? Let's just start there, okay? So I'm going to use my work energy theorem, right? All the energy in the system is here. If I look, there's a normal force and there's no friction, but over here the normal force is always, everywhere, the normal force is always perpendicular to the motion of the block, so it doesn't do any work. So when I get down to the bottom, for block M, now I'm not looking at this block right now, just for block M, it gets to the bottom, all of its gravitational energy becomes kinetic energy, and I can set this up, no work is done, so mgh equals 1/2 mv squared, and I can solve for v, right? I don't know why I have that twice. but okay, so, right, there's 200, so the total amount of energy in the system, by the way, is 200 joules, right? This mgh is 200, and that goes here, and I have things twice, I don't know why. But when you solve for v, right, that block's going to be going 10 meters per second at the bottom of the hill. Okay, 10 meters per second at the bottom of the hill, that's still 200 joules. The total system, we've kind of already talked about this, there's only 200 joules available in the whole system, right? 200 joules, 10 meters per second at the bottom. Okay, and then the things are going to collide. So let's look at, okay, so when the two blocks collide, the next question I could ask is, well, what's the maximum compression of the spring going to be? Now, this is where things get a little bit more complicated than what you could see on the exam. I'm not going to put something this tough on the exam, but I want to look at this maybe more difficult problem to kind of learn some principles, okay? So when the two blocks collide, how much will the maximum compression of the spring be? And so, I mean, this is kind of a crazy problem, okay? So this is going to slam into block N, and what I want you to think about is, at first, what will be happening to the velocities of each block, okay? And then what's happening to the energy, okay? So think about this. Block M is it's going fast, 10 meters per second. It's going to hit that spring. That spring is going to push backwards on it. So block M is going to start slowing down. But block N wasn't moving in the beginning. But as that spring starts to compress, it's going to push forwards on block N. So block N is going to start speeding up, okay? So here's what's going on. Block M is slowing down. I should not have named these M and N. The 4 kilogram block will be slowing down. The 7 kilogram block will be speeding up, okay? So let's think of it like this. Here's a force diagram to kind of show you what's going on. I've got the normal force on the weight on the 4 kilogram block, and the spring is pushing it backwards. And the other block, it has a greater normal force, a greater weight. Those are balanced, right? And the spring is pushing it forward. Now, what do these two spring forces, how do they relate? Well, they're third law pairs, right? It's the same spring. It's going to be pushing on one block with as much force as it's pushing on the other, okay? And that should tell you something, right? If this is the same force, then this is a different mass. The acceleration of this block is not going to be the same as the acceleration of this block, right? This one's going to be greater in the negative direction. This one's going to be less in the positive direction. But anyways, the point of this is that the 4 kilogram block is going to be slowing down, but the 7 kilogram block is going to be speeding up, okay? And while this is happening, okay, what's going on with the energy? Initially, this had all the kinetic energy was in the 4 kilogram block before it hit the spring. I mean, this is what it looked like in the beginning, okay? But in the end, right? In the end, both blocks are going to be moving, so they'll have kinetic energy, but I will have compressed the spring, right? When I reach that maximum compression, I will have compressed the spring. Some of the energy is going to be in the spring, so this could look, right, same total amount of energy, but maybe it's going to look something like this. A little bit of kinetic energy between both the blocks. This one's speeding up slowly, this one's slowing down, and then a bunch of energy stored in that spring, okay? Now here's where you've got to, I mean, and this is where, like, it takes a little bit of experience, and this is the piece that, like, we'd have to tell you probably, or, I mean, because you have to have some experience to kind of see this, but the moment of maximum compression of the spring will be the time so the 4 kilogram is slowing down, the 7 kilogram is speeding up, and there will be a moment where their velocities match, where they have the same velocity. And at that is the moment of maximum compression, okay? That is the moment of maximum compression, and that's going to be important for us, okay? Here we go. So at the moment of maximum compression, there's still only 200 joules in the whole system to work with, right? No work is being done by friction or anything like that, so I don't have to worry about that. I've got some kinetic energy in the 4 kilogram block, some kinetic energy in the 7 kilogram block. Now, at the moment of maximum compression, those V's will be the same, and then I've got some energy stored in the spring, okay? So do I have enough information to run this through? Not yet, okay? But this is a collision problem as well, right? There's a collision. So let's take a momentum point of view here. With a momentum point of view, right, I've got the initial momentum before the collision is equal to the momentum afterwards, and we're going to set this after point at the moment of maximum compression, okay? So in the beginning, all the momentum is in the 4 kilogram block, right? The 7 kilogram block isn't moving, okay? So I have this thing. So there's 40 kilogram meters per second worth of momentum in the system, okay? And at that moment of maximum compression, both blocks are moving with the same velocity. So it's like a perfectly or a maximally inelastic collision, right? They're moving together. There's that moment when they're stuck together where they have both the masses traveling at the same velocity, right? So we can look at this like this. So here we go. So here's this thing. And so that speed, right? I know everything but that speed. That speed where both masses are moving at the same velocity is 3.63 meters per second. And that comes out of the momentum stuff, right? And so I could base the kinetic energy, right? I could figure out my kinetic energy bucket right here. And then I've got this, and then the rest of the energy is in the potential energy bucket, right? Because there's still energy stored in the spring. Okay, so here we go. Yeah, so all this is here. Isn't that marvelous? Now let's go back to the energy calculation. So now I'm here, and I'm saying, okay, I've got this 3.63. Let's plug it in. And so we do. And I can plug in the 150, right, because it's 150 Newton meter spring. And I know everything now but X, and I can figure out what that maximum compression is, right? This is just turning the algebra crank a little bit. So 1.3 meters, this must be a really long spring. If I did all of my calculations right, 1.3 meter compression, okay? And that's just at the moment of maximum compression. The system's still moving, right? At that moment, both blocks are going this speed. The spring is compressed, but it's not just going to sit there. It's not going to stay compressed, right? What happens next? Okay, well, the spring is springs don't like to be compressed. It's going to uncompress, right? The spring is going to now start pushing the blocks apart as it tries to uncompress itself. Ooh, okay, so now this thing gets even more interesting, right? I mean, we could have been done here and been like, oh, ta-da, 1.3 meters, problem's over, right? But let's keep looking at this, right? When the spring pushes the blocks apart, okay, my first question is the energy conserved? And then again, we look at this and we say, okay, well, is there any frictional forces? Is there anything outside the spring block system in the Earth that's acting on this thing? And there's not, right? There's no friction, there's no air resistance. So the energy is going to be conserved, right? I'm going to get all my energy back, okay? So it's like I'm starting here, where both of the blocks have some of the kinetic energy. There's a bunch of the energy in the spring, and that's going to be equal to that original total amount of energy, which, if I'm remembering right, was 200 joules, okay? And it's the spring energy is going to dump itself out. So my final energy solution is going to look like this, where I have 200 joules of energy, and I've got kinetic energy now split between the two blocks. Okay, so yeah, so they come apart. Yeah, look, they came apart. So now what happens? When the spring pushes the blocks apart, is the energy conserved? Oh yes, so here it is. There's that 200 joules split between the two blocks. Okay, I know these masses, right? 4 and 7, but I don't know what these velocities are. And now I'm in trouble. I have 2 unknowns and 1 equation. I can't solve this. I can't solve this right now. And then I remember, oh yeah, well, this is also kind of like a collision problem where the things bounce. Okay, so let's go back to momentum again. So here's that energy thing just for a reference. Okay, and on the momentum side, so again, this system, if you remember, when it was just the 4 kilogram block, it had 40 kilogram meters per second worth of momentum. So they collide, the collision happens for a little bit of time, and then they come apart. So now this 40 kilogram meters per second is going to be split between the two masses, the 4 kilogram block and the 7 kilogram block, and their velocities. Okay. Here we go. And now I'm like, oh no! I still have only 1 equation and 2 unknowns. I can't solve this one either. And then you look and say, oh look, I've got an energy equation over here and a momentum equation over here. Different equations, same unknowns. So now I have 2 equations, 2 unknowns. Ta-da! I can use algebra to figure this out. And by the way, and we didn't really talk about this in class, but this is the power of elastic collision problems, is they give me a little bit more purchase. If all I had was momentum, I would be stuck here. I'd be stuck here. If energy wasn't conserved, I'd be stuck here and be like, well, I can't figure either of these out unless I have a little bit more information. But if I know that the collision is elastic, meaning that the energy is conserved, I can get another equation, and now I can figure this out, okay? Oh, and so by the way, this like 2 equation, 2 unknown system, this is way more complicated than what I would ask you to do in the exam or probably even in the homework. So I'm going to show you the math of this, but just know that I'm not going to ask you to do this, okay? But the math of this looks like this. Here's these original equations. This is messy, so I'm just going to rewrite this in x's and y's. So the velocity of the 4 I'm going to call x, the velocity of the 7 I'm going to call y. And I'm just going to reduce this. So 200 equals 2x squared, right? Because half of 4 and then half of 7. 3.5 y squared, right? And then over here, on the momentum side, I have 40 equals 4x plus 7y. Okay? So I'm going to take this and solve it for x. So I get 40 minus 7y divided by 4. Or divide that 4 over, I get 10. X is equal to 10 minus 1.75y. Okay, cool. So now I'm going to plug that in for x over here. So now I'm here. And I say, oh, look at this thing. This is a little polynomial in here. I've got 2 of these. I can multiply them together. I can FOIL them out, and when I do that, I get this, right? I can expand that expression into this because I have 2 of these expressions, so I can multiply them together and that get this. I can then multiply that 2 inside of there. And now I've got 6.125y squared, and I've got a 3.5y squared over here, so I can add those together. And I've got this 200 over here and this 200. When I subtract that over, that normally doesn't happen. It just did I just picked some numbers that, anyways. So now I've got 0 equals this. I can factor the y out. And so y is either going to be 0 or 7.27. And now here, I'm going to use my physics intuition to decide which one of these it is. It can't be 0, right? Because that spring, if you look at the previous, that spring is pushing this. The 7 kilogram block is already moving to the left. at maximum compression at like 3 meters per second in a little bit, right? And the spring is going to keep pushing it to the right. So the only one of these that makes sense is this, right? So that's so the big block, the 7 kilogram block, after the spring pushes them apart, is now going 7.27 meters per second. And then I take this and I plug it in for y here, and I can solve for the velocity of the little one. And that's going after the spring pushes them apart. It's now going to the left at negative 2.72 meters per second, while this one goes zipping off to the right. Okay. Now again, this is more complicated than anything I would ask you to do, but I just wanted to finish the problem. Anyways, I know this was really fast, but this is just, again, we're looking at different ways we can think about these momentum energy combo problems, okay? So take a look at this. I'd love to talk to any of you about it if you have any questions, but this just gives you a little bit more practice, a little bit more experience kind of looking at problems like this. I hope you're having a great day, and I'll see you in class.